In this video, we're going to talk about trigonometric substitution. This is a technique which is used to evaluate certain integrals by replacing a variable with a trigonometric function. Why would you want to do that? Well, ultimately, it's easiest to understand why you'd want to do that by trying to solve problems and seeing why it works along the way. So let's start with an example. Let's start with the integral of 1 over the square root of, let's say, 4 minus x squared dx. And let's evaluate this from -2 to 2. Suppose we want to compute this integral. The basic idea of evaluating this integral using trigonometric substitution is using some technique that allows you to take this denominator and rewrite it. You have 4 minus x squared. What you'd like to do is you'd like to rewrite it so that it's a perfect square. And in order to do that, we're going to use a trigonometric function, which will allow us to exploit certain trigonometric identities. In this particular one, we want to let x be equal to 2 times sine of theta, where theta is some other variable. Now, we don't have complete freedom over theta, but we'll come back to that in a minute. The first question you might want to ask is, why? Well, there are really two whys here. Why would you want to do it, and why are you able to do it? Let's talk about the first one first. Why would you want to make a substitution like this? The basic idea is that if x is equal to 2 times sine of theta, then x squared is equal to 4 times sine of theta quantity squared. Why is this helpful? In our denominator here, we have 4 minus x squared. So 4 minus x squared is 4 minus 4 times sine of theta quantity squared. You can factor out the 4, and what you're left with is 1 minus sine of theta squared. 1 minus sine theta squared by the Pythagorean identity is cosine theta squared. And so now you have that 4 minus x squared, which is underneath your radical, is actually equal to 4 times cosine of theta squared. And that's a perfect square, because that's 2 times cosine of theta quantity squared, like so. So now you can take the square root. The square root of 4 minus x squared is equal to the square root of 2 times cosine of theta quantity squared. And the radical cancels with the square, and you end up with 2 times cosine of theta. Well, to be precise, you actually end up with the absolute value of 2 times cosine theta, because the radical gives you the positive square root. We don't really have to worry about that. And the reason we don't have to worry about that is because of something that I said earlier about theta. We don't have complete freedom to let theta be anything. We're going to choose theta based on the possible x values that we have here. So the idea is that x goes from -2 to 2. So if you want to attain all of the values of x between -2 and 2, you need to figure out which values of theta will make that happen. And for that, you might want to think about this in another way. X over 2 is sine of theta, which means that theta is arcsine of x over 2. Arcsine. Now, arcsine is the inverse of sine, but only on a limited domain for sine. Sine is only invertible for certain values. And the values that we choose for sine are minus pi over 2 to positive pi over 2. If you remember what the graph of sine looks like, it's periodic. So in particular, it's not 1 to 1, which means that it's not invertible. So it looks something like that. Not exactly, but something like that. And this is minus pi here, and this is pi here. It goes up to 1, and the lowest it can be is negative 1. This is y equals sine of theta. Or perhaps we should say x equals sine of theta. So we're going to let this be, well, no, y equals sine of theta, where this is theta and this is y. So y goes between sine, the values of sine go between minus 1 and 1. But they do that repeatedly. In order to find an inverse for sine, you have to look at a restricted domain where this graph is 1 to 1. And usually what we do is we go from minus pi over 2 to positive pi over 2. So that means you're only looking at a small portion of the graph, this portion. And what this portion does is it hits all of the output values from minus 1 to 1. But you don't need all of the inputs. You only need a small selection of them, going from minus pi over 2 to positive pi over 2. And that's why we have that restriction on theta there. But this is perfect for us, because if we have that theta is between minus pi over 2 and positive pi over 2, then cosine is always positive there. If you remember what the graph of cosine looks like, let's change the color here, then cosine looks like this on this portion. And so cosine is always positive, so y equals cosine of theta. It's always positive on that region, so we don't need to worry about it. On the interval where sine has an inverse, cosine is always positive, so we just don't need to worry about the absolute value signs. Anyway, that answers why you'd want to do it and also why you're allowed to do it, because you're actually just looking at a small selection of x values. And these are the only x values that are allowed, because x can't be smaller than negative 2 or larger than positive 2 without giving you the square root of a negative number. So you're only interested in these values from minus 2 to 2. Now, I mentioned that sine goes from minus 1 to positive 1, but notice this is 2 times sine. Sine itself goes between minus 1 and 1, so if you multiply it by 2, then it goes from minus 2 to positive 2. Anyway, so that's why we're allowed to make the substitution that we are, and also why we want to, because it takes that radical and turns it into something much nicer. So let me just rewrite this integral from minus 2 to 2, 1 over the square root of 4 minus x squared dx. So the substitution that we want to make is x equals 2 times sine of theta. But we shouldn't forget that really what that means is that theta is arcsine of x over 2. We're going to need that fact at some point. If not for this problem, for another. So the idea here is that we want to evaluate this integral. And we want to replace that x with 2 times sine theta. But if you do that, you also have to replace the dx, which is just the derivative. So dx is 2 times the derivative sign is cosine of theta. And then put a d theta there. So now we're going to have the integral, and we'll come back to the limits of integration in a minute. And it's going to be 1 over the square root of 4 minus x squared, which we've already talked about. That's 4 times sine squared. But then you also have the dx. The dx is 2 times cosine of theta d theta. Now what about the limits of integration? We've actually already addressed those too, because x is going between minus 2 and 2, and theta is going between minus pi over 2 and positive pi over 2. Minus pi over 2, positive pi over 2. And actually you can get that from this relationship here. You say that theta is equal to arcsine of x over 2. So if you start at x equals negative 2, then theta is arcsine of negative 2 over 2, which is negative 1, and that's minus pi over 2. If x is equal to positive 2, then theta is equal to arcsine of positive 2 over 2, which is positive 1, and that's pi over 2. So that gives you your limits of integration. Since this is a definite integral, we've converted everything over to theta, so you never have to go back to the x's for this problem. So let's just compute this now. So remember, this thing right here was the reason we did the substitution. We wanted to simplify that. So we've got the integral from minus pi over 2 to positive pi over 2, 1 over the square root, and remember what 4 minus 4 sine squared was. That's this thing, 4 minus 4 sine squared. That was ultimately equal to 4 times cosine of theta squared. So this is 4 times cosine of theta squared times 2 cosine theta d theta. And the denominator here is the square root of a perfect square. So this is going to be equal to the integral from minus pi over 2 to positive pi over 2, 1 over 2 cosine theta times 2 cosine theta d theta. Well, the 2 cosine thetas cancel, and you just end up with the integral from minus pi over 2 to positive pi over 2 of 1 d theta, which is theta going from minus pi over 2 to positive pi over 2, which is pi over 2 minus pi over 2, which is pi. And that's your answer. Since it was a definite integral, we ended up with a number. We could have done this as an indefinite integral. Let's do the same integral, but as an indefinite integral. So this is the indefinite integral of 1 over the square root of 4 minus x squared dx. Now here we're just looking for an antiderivative, so we don't have limits of integration, but we can approach it in the same way. You let x be equal to 2 times sine of theta, and then dx is equal to 2 cosine theta d theta, just like it was before. So this is the integral of 1 over the square root of 4 minus x squared, so 4 sine squared, sine of theta squared, times dx, which is 2 cosine theta d theta. And all of this works pretty much the same as before. So we have the square root of 4 times cosine theta squared in the denominator there, times 2 cosine theta d theta. And just like before, the denominator is the square root of a perfect square, 2 cosine of theta, times 2 cosine theta d theta. And so the 2 cosine thetas cancel, and so you're just left with 1 times d theta, which is theta plus c. And now we need to remind ourselves what theta is equal to. Theta is equal to arc sine of x over 2. So we can just plug that back in. Arc sine of x over 2 plus a constant. If you start your problem in terms of x's, you have to go back to x's for indefinite integrals. But if you're doing a definite integral, just change everything to theta and you're fine. And so this gives us our antiderivative. Now, in fact, we didn't have to use trigonometric substitution to do this problem. You could have done a regular substitution, because we know that the derivative with respect to x of arc sine of x is equal to 1 over the square root of 1 minus x squared, which is very close to the thing we were integrating, which is why our antiderivative was arc sine of something, arc sine of x over 2. So you could actually use a u substitution instead. So we could have used a regular substitution. Or what's sometimes called a u substitution, because it's very common to use the letter u. So if you have the integral of 1 over the square root of 4 minus x squared dx, you want to make this 1 over the square root of 4 minus x squared look like that. And it's not trivial, but it can be done. Basically, the idea is you want to factor out a 4. So how does that work? 1 over the square root, factor out a 4. And what you're left with is 1 minus x squared over 4 dx. So if you take out that 4, you're going to have 1 over, and 1 over the square root of 4, that's going to give you a 1/2. times the square root of 1 minus x squared over 4 dx. And now here, that's going to be your u squared term. You want to just rewrite it. Let me take out the 1/2. Then it's the integral of 1 over the square root of 1 minus, and then we write x over 2 and square that dx. So now you can let u be equal to x over 2, and then du is dx over 2. Well, there's your dx and there's your over 2, so let's just put it back in. 1 over the square root of 1 minus x over 2 quantity squared times dx over 2. That's your du right there. And this thing is 1 over the square root of 1 minus u squared. That's that one. So what do you end up with? The integral of 1 over the square root of 1 minus u squared du, which is arc sine of u plus a constant. And then you just have that u is equal to x over 2, so you just plug that right back in there, and then you have arc sine x over 2 plus c, which is the same thing that we had before, right up here, as you can see. It's possible to do this when using a regular substitution, but it's a good example of how trigonometric substitution works. There are certainly other examples that we can look at that are similar, but don't allow for an easy u substitution. Let's do another example. Let's see, we've done b, so let's do c. So let's say the integral from, well, let's do an indefinite integral. X over, let's say actually x squared over the square root of 9 minus x squared dx. This one would be a little bit more difficult to do using a regular substitution, although it's not impossible. How are we going to go about doing this one? Well, let's let x be equal to 3 times sine of theta. I'm picking a 3 there because I've got a 9 there. When I square this, x squared equals 9 times sine of theta quantity squared. I need to have that 9 there to match up with that 9. So that's why there's a 3 in front of here. The 3 matches this 9 because I'm going to square it. So now we have 9 minus x squared is 9 minus 9 times sine theta squared. And again, using the Pythagorean identity, this is 9 times cosine theta squared. So what this is going to give us is this is going to give us the integral of, well, x squared is going to give us 9 times sine theta squared divided by, and then here we have the square root of 9 minus x squared. So that's the square root of 9 times cosine of theta squared times, now we also need a dx. So we need a dx as well, and we get that, of course, by differentiating this x. So dx is 3 times cosine of theta d theta. So what we're going to do now is we're going to just plug all that in here. So into here. So it's going to be times 3 cosine theta d theta. All right. So let's simplify it. We have the integral 9 sine theta squared divided by, and we have the square root of a perfect square. That's going to be 3 cosine theta times 3 cosine theta d theta. The 3 cosine thetas cancel, and you're just left with the integral of 9 times sine of theta squared d theta. And this is something we've done before. We've done integrals like this before. So let's take out the 9, and this is the integral of sine squared. And I'm going to use the fact that sine of theta squared is 1/2 times 1 minus cosine 2 theta. So I'm going to use one of these double angle identities. So 1/2 1 minus cosine 2 theta d theta. So let's take the 1/2 out, and we have 9/2. the antiderivative of 1 with respect to theta is going to be theta, and then we're going to have minus sine of 2 theta over 2 plus a constant. Now, if you're not really comfortable with that, you can do a little substitution there where u is equal to 2 theta. So u is equal to 2 theta, and then du is equal to 2 d theta. So there's your d theta. You have to multiply and divide by 2, and that's why you have that 2 there. Okay, so now we're done with the integral. There's no integral anymore, but we have thetas here. We need to get rid of those thetas and put them back in terms of x's. So let's just remind ourselves what x was. X is equal to 3 times sine of theta. So any place you see a theta, you can replace it with x over 3, and that's going to be sine of theta. And so theta is arcsine of x over 3. So any place you see a theta on its own, you can just replace it like that. Well, what about this sine of 2 theta? So far we have 9/2 times theta, which is arcsine x over 3, minus, but we still have the sine of 2 theta over 2 to deal with. And for that, we need to use a different trig identity. For that, we're going to use a half-angle identity. So we're going to have, let me just rewrite this as theta again, minus, so I'm going to take this sine of 2 theta, and I'm going to write it as 2 times sine of theta times cosine of theta, like that, and divide that by 2. So this 2 is that 2. The identity that I've used is that sine of 2 theta is equal to 2 times sine of theta cosine of theta. That's a half-angle identity because I went from 2 theta to 1 theta. So that's a half-angle identity. And now we just have a plus c. So we know what theta is. Theta is arcsine x over 3. We also know what sine is because we know that x is equal to 3 sine theta. X is equal to 3 sine theta. So that means that x over 3 is sine of theta. And that's what we have right there, sine of theta. So that's x over 3. That 2, of course, cancels with that 2. The only question is about that cosine. Well, if you know what sine is, then you know what cosine is because of the Pythagorean identity. We can actually also think about it in terms of a triangle, a right triangle. So let's just draw a right triangle here. Let's suppose that that's our angle theta. We know that sine of theta is x over 3, but sine of theta is, in terms of right triangles, is the opposite over the hypotenuse. So it's x over 3. X is the opposite side and 3 is the hypotenuse. So what does that tell you about the other leg? Well, by the Pythagorean theorem, this is the square root of 9 minus x squared, because we know that a squared plus b squared has to equal c squared, which is 9. So cosine of theta is adjacent over hypotenuse. But the adjacent side is the square root of 9 minus x squared, and the hypotenuse is 3. So that's our cosine theta, and that can go right up there. So what do we have? We have that our integral is 9/2 times arcsine x over 3 minus x over 3 times the square root of 9 minus x squared over 3. Plus a constant. You can simplify this a little bit because you have 3 times 3 there, and you have a 9 in the numerator. So this can simplify a bit, but let's just leave it like this. We use a sign substitution when we have a term like the square root of c squared minus x squared. And the reason we use a sign substitution here is that this term resembles the side of a triangle, of a right triangle, just in the way that we saw here. So if we draw a triangle, a right triangle, just like the one that we drew before. We let this angle be theta, and we let C be the hypotenuse, and x be the opposite side. Then the adjacent side is the square root of c squared minus x squared. This is just the Pythagorean theorem. This is what you could call A. And so you have a squared plus x squared is equal to c squared. So the square root of c squared minus x squared plus x squared is c squared. Because this term right here is c squared minus x squared. So the minus x squared and the plus x squared cancel, and you're just left with c squared. So in a case like this, then you have that sine of theta is equal to the opposite side over the hypotenuse, which is x over c. So you have that x is equal to c times sine of theta. And that's the substitution that we use. So you use that whenever you have a term that looks like the square root of c squared minus x squared. It doesn't necessarily have to be a square root. You can also use these types of substitutions in other contexts. For example, we're now on example D here. We could do something like the integral of 1 over, let's say 25 minus x squared to the 3/2 dx. This isn't exactly a square root, but it does have a root in there. The 3/2, the halves is a square root. Something like this you could also do using a trigonometric substitution. X equals, in this case, it's going to be 5 times sine of theta. And dx is 5 times cosine of theta, d theta. So now if we plug all of this stuff in, we'll have 1 over 25 minus 25 sine squared, and all of this is raised to the 3/2 times dx, which is 5 times cosine theta, d theta. So this is the integral of 1 over, and this term in here is exactly 25 times cosine theta squared. And now we want to raise that to the 3/2 power times 5 cosine theta, d theta. Let me just fix this parenthesis there. So if you raise something to the 3/2 power, that's like taking the square root and then cubing it. So you're going to have the integral of 1 over the square root of 25 is 5, and then we cube it. So 125 cosine theta, and so you multiply the exponents and you get the third exponent, times 5 cosine theta, d theta. So we can simplify this. This is the integral of 1 over 5 into 125 is just going to give you 25. And then same with the cosine. You're going to have cosine theta squared, d theta. Don't be put off by that cosine theta squared in the denominator. That might look troubling at first, but this is 1 over 25 times the integral of secant squared, d theta. Secant is 1 over cosine, so secant squared is 1 over cosine squared. And this actually has an elementary antiderivative because that is just the tangent of theta. So it's 1 over 25 times tangent of theta plus a constant of integration. Now we need to figure out what that tangent of theta is in terms of x, but again we just use our triangle. We draw a right triangle here. This is our angle theta, and sine of theta is x over 5. So that's the opposite over the hypotenuse. And the adjacent side is going to be the square root of 25 minus x squared, just like it was before. So tangent of theta is opposite over adjacent. So that's just going to be x over the square root of 25 minus x squared. So we just plug that in, and we have 1 over 25 times the opposite, which is x, over the adjacent, which is the square root of 25 minus x squared, plus a constant. And there you have it. You want to be careful when you're doing a substitution to make sure you're doing the right one. Let's look at another example, e, which is similar, at least in appearance, to the previous one. The integral of 1 over, and again we'll do this to the 3/2 power, but instead of having 25 minus x squared, it's going to be x squared minus 25 dx. Now this problem on the face of it looks the same, but it's quite different because we've changed the order of the x squared and the 25. Now why does that matter? In our previous example, example D, we wanted x to be equal to 5 times sine of theta. Now the thing about 5 times sine of theta is this value is always between minus 5 and positive 5. And that was important because that meant that 25 minus x squared was always non-negative. And that's important because we're taking the square root. So you want x to be between minus 5 and 5. However, here you don't want that. Here you want x squared minus 25 to be not less than 0, but you want it to be greater than 0 or equal to. So what that means is that x squared is greater than or equal to 25. So that means that either x is bigger than 5 or x is less than negative 5. So let me just fix my 2 there. 25. So we have to have x away from 0. Sine always passes through 0, but something else doesn't, and that something else is secant. So what we're going to do is we're going to let x be equal to the secant of theta in this case, because, well, I need a 5 in front of that. Because if you look at the graph of secant, it's always bigger than 1 or less than negative 1. So when you multiply it by 5, you get exactly this sort of picture. All right, well, if x is 5 secant theta, then dx is equal to 5, and the derivative of secant is tangent times secant. And then we have a d theta at the end. And so if you plug all of this stuff in, you're going to have the integral of 1 over, and again, it's going to be raised to the 3/2 power, but it's now x is equal to 5 secant. So it's going to be, if we square that, x squared is going to be 25 times secant theta squared minus 25 to the 3/2 times dx, which is 5 tangent theta secant theta d theta. All right. Now here we have to use our modified version of the Pythagorean theorem. So remember, the Pythagorean theorem says that cosine squared plus sine squared is equal to 1. So if you divide everything by cosine squared, so if you divide this one by cosine squared, and this one by cosine squared, and this one by cosine squared, you end up with 1 plus tangent squared equals secant squared. And that's our alternate form. Now the way that we're going to use it here is actually by subtracting that 1 away. So you have tangent of theta squared is equal to secant theta squared minus 1. And that's the form that we want to use right here, or perhaps I should say right there. So we're going to have the integral, and then in the denominator, you can factor out that 25. So you'll have 25 times secant theta squared minus 1. And all of this is raised to the 3/2 power. And it's all underneath, or in the denominator, times 5 tangent theta secant theta d theta. But this term, this secant squared minus 1, that's tangent theta squared. So what do we have? We have the integral of 1 over 25 tangent theta squared, all that to the 3/2 power, times 5 tangent theta secant theta d theta. So let's simplify this just a little bit by using that exponent there. So we're going to have the integral of 1 over, so you multiply exponents together. So this is going to be 25 to the 3/2 is 5 cubed. And then you have tangent, again you multiply the 2 by the 3/2 and you get cubed, times 5 tangent theta secant theta d theta. So this tangent is going to turn that 3 into a 2, that 5 is going to turn that 3 into a 2, and you're going to end up with the integral of 1 over 25 times 1 over tangent theta squared times secant theta d theta. Now at first glance this might seem like a hopeless problem, but if you just turn everything back into terms of sines and cosines, it's not so bad. So this is the integral of 1 over 25, and tangent is sine over cosine, so 1 over that is going to give you cosine over sine. It's cotangent, but you need to square these. And secant is 1 over cosine d theta. So that cosine is going to cancel with one of those, and you're going to have the integral of 1 over 25 times cosine of theta secant theta, not secant, rather sine theta squared d theta. And now we're going to use the substitution. You let u be equal to sine of theta, and then du is equal to cosine theta d theta. And we have that cosine theta d theta right there. So it's the integral of 1 over 25 times 1 over sine, which is u, squared du. So this is going to give you 1 over 25, and the antiderivative u to the negative 2 is minus 1 over u plus a constant. So now we just remember that u is equal to sine of theta, so we have minus 1 over 25 times 1 over sine of theta plus c. Now you mustn't think that you're done here, because you still have to get rid of that theta. So how do you get rid of the theta? Well, you have to go back and remind yourself what the original substitution was. The original substitution was that x is equal to 5 secant theta. So x is equal to 5 times secant theta. So another way of writing that is x over 5 equals secant theta. But secant is 1 over cosine, so 5 over x is cosine theta. So again, we can draw a right triangle, like so. We have a right triangle. This is our angle theta. But now, cosine, which is adjacent over hypotenuse, gives us 5 as the adjacent side, and the hypotenuse is x. And the opposite side is going to be x squared minus 25. Now that shouldn't be a surprise, because that was exactly what motivated this problem to begin with, x squared minus 25. We wanted to write that as a perfect square, which we were able to do. So it shouldn't surprise us that that shows up again here. So now what we want is we want sine, and sine of theta is equal to the opposite over the hypotenuse is the square root of x squared minus 25 over x. Now actually we want to put that in the denominator. So we're going to have minus 1 over 25 times 1 over the square root of x squared minus 25 over x plus c. And if you divide by a reciprocal, that's the same as multiplying by x over the square root of x squared minus 25 plus c, and that's your answer. So you want to use a secant substitution when your denominator has some term that resembles the square root of x squared minus 25. So this looks like the side of a triangle, of a right triangle. Just like when we were doing sign substitutions, here it was the base of the right triangle, 25 minus x squared in the square root. So that looks like the base. Here we were looking at something that looked like the altitude. There's one other thing left, which is the hypotenuse, and that can be dealt with using a tangent sub. So use a tangent substitution when there are terms that look like square root of x squared plus, say, a squared. So what do I mean like that when I say something like that? Well, we're imagining that we have a triangle again, a right triangle, and this is our angle theta. And in this case, we have an a here and an x here, and now this is the square root of a squared plus b squared, a squared plus x squared, or x squared plus a squared. That doesn't really matter. So in this particular case, we're looking at tangent of theta, which is opposite over adjacent, so it's x over a. So in this case, we have that x is equal to a times tangent theta. Now this is useful for us because if you have x equals a tangent theta, then x squared is equal to a squared tangent theta squared. So x squared plus a squared is equal to a squared tangent theta squared, plus a squared. And now you can factor out that a squared, and you're left with tangent theta squared plus 1. And this should look familiar because we saw that just up here where we saw that tangent squared plus 1 is secant squared. Tangent squared plus 1 is secant squared. So we have a secant squared here. So once again, we've taken our x squared plus a squared and we've made it look like a perfect square. Secant squared. And there's an a squared in front. A squared. And that's really the whole idea. You start with some term that's square root of x squared plus a squared, and you want to make that look like a perfect square. And using the right substitution does that. Now it looks like a squared secant theta squared, which is the square of a perfect square. So it's a times secant theta. So now what we're using here is a tangent substitution, which is that one. Let's look at an example. So I forget what number or what letter we're on. I think we just did E, so let's do F. So F is the integral. Let's keep it simple. The square root of x squared plus, let's say, 4 dx. So in this case, our a is equal to 2. So a is equal to 2. So your x is going to be 2 times tangent theta. And then dx is going to be 2 times the derivative tangent, which is secant squared d theta. So what we can do now is we can plug this all in to our integral. And so we have the integral 1 over the square root of x squared, which is 4 tangent theta squared plus 4, times dx, which is 2 secant theta squared d theta. And as we've just discussed, tangent squared plus 1 is secant squared, so this is a 4 times that. So we're going to have the integral of 1 over the square root, factor out the 4, and you'll be left with tangent squared plus 1, which is secant squared, secant theta squared, times 2 secant theta squared d theta. So we've taken this x squared plus 4 and we've rewritten it as a perfect square. So this is going to be equal to the integral of 1 over the square root of 4 is 2, the square root of secant squared is secant, times 2 secant, but now we have secant theta quantity squared, d theta. This 2 cancels with that 2, this secant cancels with one of those, and you're left with the integral of secant theta d theta. And this is one that we know how to do. If you look back, when we were talking about substitutions, we actually did this one before. It's not a trivial one by any means. This is the natural logarithm of the absolute value of secant theta plus tangent theta plus c. So we need to figure out what all of these terms are in terms of x. Well, tangent we already know, because we know that x is equal to 2 times tangent theta. So that means that tangent theta is equal to x over 2. We still need to figure out what secant is, but that's what the triangle is for. So we draw our triangle again. It's the same triangle, really. It's just an arbitrary right triangle. And tangent of theta is the opposite over the adjacent. And the hypotenuse is a squared plus b squared, and then you compute the square root of that. So it's going to be 4 plus x squared. Now secant is 1 over cosine, so the first thing you can do is write down cosine. Cosine is adjacent over hypotenuse, which is 2 over the square root of 4 plus x squared. That's cosine. Secant is 1 over that. So secant theta is the reciprocal, square root of 4 plus x squared over 2. And so that one goes into here, and tangent goes right there. So you're going to end up with ln of the absolute value of secant, which is the square root of 4 plus x squared over 2, plus x over 2, plus a constant. And that is your antiderivative. So we have different kinds of substitutions now. You have a sign substitution, and you usually want to use that when you have something that looks like c squared minus x squared, usually in a square root. And the idea is that you want x squared to be smaller than c squared, and sign is the one that's bounded between minus 1 and 1, so that's the way to do that. You use a secant substitution when it's the reverse, so it looks like x squared minus something like c squared. This is the reverse situation. Now you want this to be positive, so you need x squared to be big, and secant is the one that gets big. It stays away from 0. And then you have tangent, and you want to use that when you have something that looks like the square root of x squared plus a squared. And in this case, you don't necessarily have to worry about a square root being there, but the idea is usually that you want to try to write something as a perfect square. And in this case, you don't have to worry about x being big or small. It can be anything, and tangent has that property. It can be small, it can be large. So these are your 3 trigonometric substitutions. So these are the trigonometric substitutions that you might want to use.